welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 1615, Maximal Network Rank. Before we get into the question prompt, I just want to say please subscribe to the channel. I'm so close to 1,000 subscribers and I need you guys to help me get over that line. So please drop a sub so we can hit that milestone. Otherwise, let's read the question prompt. There is an infrastructure of n cities with some number of roads connecting these cities. Each roads of I equals A of I, B of I indicates that there is a bidirectional road between cities A of I and B of I. The network rank of two different cities is defined as the total number of directly connected roads to either city. If a road is directly connected to both cities, it is only counted once. The maximal network rank of the infrastructure is the maximal network rank of all pairs of different cities. Given the integer n and the array roads, return the maximal network rank of the entire infrastructure. So let's look at an example. So essentially, for this question, sample infrastructure, our solution should be 4. And why is it 4? Well, if we choose nodes 0 and 1, then there are 4 roads connecting them, right? So from 1, there's a road to 2, there's a road to 3, and there's a road to 0. So that's 3 rows in total, right? And then from 0, there's a road to 3, and there's a road to 1. But obviously, we've already counted this road, so we don't count it twice. And we just count this one, so we get 3 plus 1 equals 4. So if we had chose 0 and 3, there would only be 1, 2, 3 roads. That's not good. If we chose 1 and 3, then there's 1, 2, 3. That's not the best answer. 1 and 2, there's 1, 2, 3. And on and on and on. So sorry, there's 3 here. So this road, and this road, so that's 3. So obviously the maximum is 4. So this question seems really complicated. How the hell are we supposed to do this? But if you boil it down and figure out actually what you need to do, it's super simple. What you need to do is just find out how many edges go from each node, and then for all possible combinations of 2 cities, just sum all of the edges together, and that is your answer, right? But you do need to be careful that if the two nodes are actually connected by an edge, you need to subtract one because you can't double count. So you just need to remove one, and that's just going to be your answer. You're going to take all pairs of nodes, all of the edges they have between them, add them together, and then subtract one if they're connected. And the way that we're going to do this is we're going to build a graph. So the key of our graph dictionary here is going to be a node, and the value here is going to be a set of all of the nodes it's connected to. So we're going to call this connections. So we're going to build this dictionary, and then what we're going to do is we're going to take all node pairs, so we'll call this node 1, node 2, and we're simply going to sum the length of all of their connections. And then because we used sets here instead of a list, we can actually do an O of 1 lookup to see whether or not this node 1 has node 2 in it, and vice versa. If it does, then that means that they have a connection, and we don't want to count those connections twice. So we simply need to return 1. If they don't have the connection, then we don't have to make that adjustment, and we just do this for all node pairs, and there's your solution. This question is a lot harder in text than it actually is in code, so let's code this up and get our solution. It's quite simple. I'll see you back in the editor. Back in the code editor, let's code this up. This solution is actually really simple, and it's one of my favorite types of problems because you take some sort of input and you make a graph. So let's create our graph. So we're going to say graph is going to equal collections.default dict, and remember that we want to use sets here as the values for our dictionary. So now what we need to do is build our graph, and remember that the structure is that roads of I indicates that there is an edge between city A of I and B of I. So we're going to say for city 1, city 2 in roads, we're going to say graph. So city 1 has an edge to city 2. City 2, where's city 2? And then we're going to say graph of city 2 dot add city 1. So now we've made the connection between the 2 cities. Now what we need to do is just set up a little variable to keep track of our solution. So we're going to set it equal to 0 because obviously we haven't computed any network rank yet. Now what we want to do is go over all combinations of two cities and basically figure out the maximum network rank. So the way that we're going to do that, we're going to say for city 1, city 2 in itertools.combinations. So we want to make all possible combinations of essentially, let's see, of each of the cities. So this is going to be graph.keys because those are all the cities that we have. And then we obviously want to do combinations of 2. If your language doesn't have a helper function to basically calculate all of these combinations, then you'll have to do it by hand. But luckily we're using Python, so we can just use this nice helper function. Otherwise, you just need to figure out how to do all the combinations, but it's pretty straightforward. Anyway, remember that our network rank is computed by taking all of the connections for one city plus all of the connections in a second city and then summing them together. And we need to basically discount the fact if a road connects both cities, we only want to count it once, right? We don't want to count that same road twice. So let's check whether or not we have a connection between the two cities. So we're going to say has connection is going to equal to 1 if city 1 is in graph of city 2. So what we're doing is we're checking whether city 1 is one of the cities that city 2 has an edge to, right? And that's the reason that we use sets here, so we can perform this lookup in constant time. If we use the list, obviously it would take big O of n time, so we want to use that constant time lookup, which is why we use the set here. So if we have that connection, then we're going to say it's 1, otherwise it's 0. So basically, how much do we need to subtract from our sum if there's that connection? If there's no connection, we don't need to account for that, so we can just subtract 0. If there is a connection, that means that we'll have counted a road twice, so we need to subtract 1. So what we're going to do now is we're going to say the number of connections that city 1 has. So city 1 connections is going to be equal to the length of graph of city 1. So basically, I'm going to count how many connections it has. And then city 2 connections is going to be the same thing, is going to equal to the length of graph of city 2. And now what we need to do is just say the result is going to be the maximum of our current result. And what is it going to be? City 1 connections plus city 2 connections. And then we want to minus, accounting for whether or not there's a connection between city 1 and city 2. So we're going to say minus has connection, and that will take care of double counting an edge if we had done that. And then that's all we need to do. We simply return our result at the end, and we are good to go. So we can submit this, and once this runs, we can see that, hello, Leetcode, taking forever. Cool, it works. So what is the time and space complexity for our algorithm here? Well, we know that we have to check all possible combinations of city 1 and city 2, which basically means that we need to try all the connections between cities. In the worst case, every city will be connected to every other city, which means that we're going to have to check big O of n squared connections here in the worst case. So that's going to be your time complexity, and the space complexity is going to be the same. In the worst case, every city will be connected to every city, which means that our graph, for every node, we're going to have to store every basically n-1 connections in this set here, which means that we're going to have n times n-1 for the storage, which asymptotically is just going to be n big O of n squared. We can get rid of that little constant minus n because obviously n squared is bigger than n. So that is going to be your time and space complexity. Like I said, really straightforward problem. This is one of my favorite types of problems. I love when we get some sort of input and it's a list and we have to transform it into a graph and then do something with that graph. You see this pattern so much across so many companies. They love to ask this kind of one. It's a really good question to test your knowledge of graphs and how you traverse them. And this question is no exception. So that is how you solve this question. If you like this video, please leave a like and a comment. It really helps with the YouTube algorithm. If you want to see more content like this, like I told you in the beginning of the video, please subscribe to the channel. It really helps me out. We're so close to 1,000 subscribers. Please help me get there and grow even further. Otherwise, thank you so much for watching. If you made it this far, thank you and have a great rest of your day.